Redox titrations. The strength of a reductant or oxidant can be determined volumetrically using redox reactions. Okay, first titration is permanganate titration. Or permanganometry. Okay, permanganate titration or permanganometry. Here permanganate solution, that is KMnO4 solution, is used as the oxidizing agent, which is titrated against reducing agents like FeSO4, oxalic acid, H2C2O4, etc. These are used as reducing agent. The titration is taking place in the acidic medium. Okay, and endpoint is the appearance of a pink color. Okay, here KMnO4 solution is colored. Okay, so it is used as self indicator, and endpoint is the formation of pink color. Okay. For example, if we are titrating MnO4 solution against H2C2O4 oxalic acid. Okay, in this reaction, while titrating, KMnO4 is taken in a burette whose normality is known. Okay, let it be N1. And V1 is the volume after the formation of the pink color. Okay, V1 is the volume of KMnO4. Then H2C2O4 is taken in a pipette whose volume V2 is known. Okay, using pipette, H2C2O4 is taken in conical flask. Then titration is started, and the final point is the coloration, or the at the equivalence point a pink color is obtained. Okay, at the equivalence point, gram equivalence of KMnO4, is equal to gram equivalence of H2C2O4. It is oxalic acid. Okay, so the gram equivalence of KMnO4 is V1N1, which will be equal to V2N2. Okay, V1N1 and V2 are known quantities. Okay, from which N2, the normality of oxalic acid, can be calculated. Okay, like this, using this permanganate titration, we can find the strength or normality of reducing agents like oxalic acid, FeSO4, etc. Second titration is dichromate titration or dichrometry. Here potassium dichromate K2Cr2O7 is the oxidizing agent, which is titrated against reducing agents like FeSO4, then oxalic acid, oxalate, etc. Okay, here the reaction is taking place in acidic medium. K2Cr2O7 is not a self indicator, so here we are using diphenylamine as indicator. Diphenylamine K3 FeCN 6 times. Okay, so after titration, at the end point, diphenylamine gives a blue color. Okay, so the end point can be determined because the reactant oxidizes diphenylamine and form a deep blue color to the solution. So by using the same equation V1N1, so V1N1 and V2 is known. So by using this, normality of FeSO4 or H2C2O4, the reducing agents, can be calculated. Like this we can find the normality of the reducing agents using dichromate titration or dichrometry. Okay. Third one, iodometry. Here starch is used as an indicator with reagents which can oxidize I- ions. Example, Cu2+. Cu2+ can oxidize I- ions. So in such cases we are using starch as the indicator, because during this process, during this reaction, iodine is liberated. That is 2Cu2+ plus 4I-. This reaction takes place and iodine is liberated. Okay. Starch gives a blue color with iodine. Okay. Starch gives blue color. So after the liberation of iodine, we are adding starch. So a blue solution will be obtained. Then next what happens? We are titrating this solution against thiosulfate. Thiosulfate consumes this iodine and the end point will be the disappearance of blue color. Okay. Disappearance of blue color will be the end point, because thiosulfate consumes the iodine produced, and at last the end point there will be no iodine and starch gets decolorized. Okay. So the reaction will be I2 with S2O3 2- gives 2I- plus S4 O6 2-. This reaction takes place. So there will be no iodine left. So the color changes, disappear. The blue color is disappeared. Okay. Similarly, here also we can find the normality using the same equation. V1N1 is equal to V2N2. Okay. Next is limitations of concept of oxidation number. Okay, it is difficult to classify redox reactions according to the different approaches like classical, electronic and oxidation number. And oxidation number. Okay, so to overcome this, redox process are determined in terms of change in electron density. Okay, change in electron density. Okay. This is one of the limitation of oxidation number. Okay, so the redox process was explained in terms of change in electron density. So according to this, oxidation is the process in decrease in electron density and reduction is the process in which increase in electron density. For example, in the formation of Na+, this is oxidation because there is decrease in the electron density of this atom, and in the case of Cl- ions, reduction occurs because there is increase in electron density. This is one of the limitation of concept of oxidation number. Okay.